All right, so we've been talking about muscles and muscle contraction. I want to talk about just a couple of more things to consider about muscles, and one of those is muscle tone. Right? In physiology, we think a lot about an animal's energy budget. In fact, that's kind of a whole branch of physiology, is just looking at energy budgets. And the best way to sort of think about an energy budget and what an animal does with its energy is to think about your own budget that you have. Except that your budget is with your paycheck, right? So when you get paid, you are going to pay your rent, you're going to buy gas, you're going to buy groceries, you're going to buy all of these things that you have to buy, have to pay for. And then hopefully, if there's a little bit of money left over at the end, you can have some fun with that, right? And muscle tone has to do with an animal's energy budget, because an animal is going to do just about the same thing with its energy that you do with money. It's going to partition it in certain ways. Let's think about what we need energy for, right? Well, we need energy to exercise. We need energy to do all of these other things, like reproduce, like look for food, maintain our tissues and things like that. And tissue maintenance has a fairly high cost associated with it. Muscles are a large proportion of your body mass. So in the interest of saving energy, what's going to happen is that if you aren't using a muscle, your body is going to stop maintaining it, right? It's kind of like you, right? If you're not using that Netflix subscription, why are you paying for it, right? Stop paying for it, use the money somewhere else. And your body does the same thing. So when a muscle is not being used, it's not going to be maintained, and it's going to get smaller as a result of that. Muscle tone is an effort to avoid that atrophy. Okay, that atrophy. And some of you have probably experienced atrophy before. If you've ever broken a bone and had an arm or a leg or something like that in a cast, you noticed that when you got the cast off, the muscle was much smaller. All right? Well, what happened is that when you were in that cast, your body said, hey, this muscle's clearly not being used. Why are we wasting energy to maintain it? And as a result of that, the muscle got smaller, right? So that's essentially what we have here, is we have muscle tone as an effort to avoid atrophy. When a muscle is not being used, you are going to go through a sequential stimulation of motor units. That is going to cause very small contractions in the muscle. Causes small contractions in the muscle. And that's why on the previous graph that I showed you, even in a relaxed muscle, we have a small amount of tension because of this muscle tone. So what your muscles do is they go through from motor unit to motor unit to motor unit and cause these very small contractions, exercising those muscles and thus avoiding muscle atrophy. All right? A lot of times people who stimulate their muscles more by exercising have more of these sequential contractions that are occurring, and as a result of that, they typically have more muscle tone. Right? A little bit later on in the semester, when we look at smooth muscle, we're going to see that muscle tone takes on a slightly different meaning, because you can tonically contract a smooth muscle for days in some cases. But in skeletal muscle, this is what we're talking about. Okay. I want to talk about just a couple of other things here related to skeletal muscles. Right? The next one that I want to talk about is the fact that we have more than one type of contraction. Right? In skeletal muscles, we have what we call isometric contractions, and we have isotonic contractions. Okay. So far, I've talked about a couple of different things, right? I've talked about holding a glass of water or holding a book, right? If you were holding a book in one place, right, I ask you to flex your elbow and I ask you to hold that book with your elbow at 90 degrees, all right? What you're doing is you're doing an isometric contraction, okay? That word isometric, iso means same, metric means length. So we're holding the muscle at the same length. All right? An isometric contraction holds the muscle at the same length. So this would be like flexing your muscles, okay? Or holding a book or something like that with your elbow flexed, pushing against a wall. The wall isn't going anywhere. The muscle's not changing length, but there is tension on the muscle. All right? Now, by contrast, I could give you a barbell, for instance, and ask you to start doing curls with that barbell. When you do that, your biceps are going to start moving the barbell towards you. All right? They're going to shorten and they're going to have tension on them. If you're doing that sort of a contraction, that's called an isotonic contraction. Okay? So this is same tension. And this involves movement. Okay, this involves movement. So we have isometric contractions in which there is no movement, but there is tension. And then we have isotonic contractions where there's tension and movement, right? And that would be bringing a barbell towards you or lifting a cup of coffee to take a drink or something like that. This would be holding the cup of coffee or holding the barbell for your friend or the plate for your friend while they're doing their lifts at the gym, right? Okay, so those are just a couple of things that I wanted to sort of point out regarding isometric and isotonic contractions. The very last thing that I want to talk about regarding muscles is I want to talk about that twitch speed that we mentioned a couple of minutes ago. Remember when we drew a muscle twitch, we gave it a time range. I think I put 50 to 100 milliseconds. I think your book gives 10 to 100 milliseconds. But regardless of what the range actually is, it's important to understand that some muscles have a fast twitch speed and some muscles have a slow twitch speed. And rather than write all of this out, I'm just going to show you the table in your book that's relevant to this and kind of go through it with you. This table, 12. So I'd mentioned that muscle fibers can contract with different speeds. When we talked about twitches, we talked about how some of them have a slow twitch, some of them have a fast twitch. And this has to do with different, what we call fiber types in skeletal muscles. Rather than write all of this out or try to draw it out, even though there's really nothing to draw, I'm just going to refer you to page 392 of your textbook. This is table 12.2, and it talks about the different muscle fiber types, and this really summarizes everything quite well. So generally speaking, in our skeletal muscles, we have three different types of muscle fiber. We have what we call slow twitch oxidative fibers, or type 1 fibers. We have what we call fast twitch oxidative glycolytic fibers, which are what we call type 2A fibers. And then we have fast twitch glycolytic fibers, which are type 2B fibers. And these vary in their twitch speed. The slow twitch fibers, as the name implies, contract slowly. They have a slow twitch. So they would be out there on that 200 millisecond range. Whereas the fast twitch fibers are going to contract the fastest. They're somewhere around 10 to 50 milliseconds in terms of their contraction speed. So we do see a variation. Of course, the fast twitch oxidative glycolytic would be in the middle. So these muscle fiber types vary in a number of ways beyond just their twitch speed, although those other ways that they vary all contribute to that twitch speed. All right? The biggest difference, the reason that we see a different twitch, is we see different isoforms of enzymes present in these muscle fibers. So, for instance, myosin ATPase, which is the enzyme that hydrolyzes ATP during a muscle contraction, acts fairly slowly on slow-twitch oxidative fibers, but the isoform that we find in fast-twitch muscle fibers is much faster. It hydrolyzes that ATP more quickly, and as a result of that, we see a faster twitch. All right? Similarly, in order to relax the muscle and end the twitch, we have to reclaim calcium back into the sarcoplasmic reticulum. The enzyme responsible for that is calcium ATPase. We see that it acts a lot more quickly in fast-twitch muscle fibers than it does in slow-twitch muscle fibers. All right? All right, so what are some of the characteristics of these muscle fiber types beyond just their twitch speed? Okay. One of the things that we do see that slow-twitch muscle fibers tend to be fairly resistant to fatigue. Right? They have more endurance than we see in the fast-twitch oxidative glycolytic or the fast-twitch glycolytic fibers. Much more endurance. So as a result of that, they are very commonly used in our body. We use them for posture, we use them for endurance activities like going for a run and things like that. The fast twitch fibers are used during burst activity, things that aren't going to last a long time because they don't have a lot of endurance. And we also see them for quick movements. So think about the muscles that control your eyes, for instance. Those are great examples of places where we find fast twitch muscle fibers. Okay. The name slow twitch oxidative also implies how this muscle fibers get their energy. All right? These guys are largely oxidative and aerobic muscle fibers, meaning that they're relying on oxygen, they're relying on the mitochondrial enzymes that we talked about earlier in order to get their energy. All right? This is what prevents them from fatiguing quickly as well. All right? The glycolytic muscle fibers, glycolytic, splitting sugar, are doing anaerobic glycolysis, and as a result of that, they're building up lactic acid faster and they fatigue more quickly. Because the slow twitch muscle fibers are oxidative, they require a constant supply of, first of all, fuel, but also oxygen. So we do see a lot of blood going to these muscle fibers. Because there is a lot of blood going to them, they kind of take on a dark appearance as a result of that. We often call this red muscle. On top of that, these slow twitch oxidative fibers also have a lot of protein called myoglobin in there, which is an oxygen binding protein, and it also has a red color, and as a result of that, it contributes to the dark red color of these muscle fibers. Because these glycolytic fibers have very little reliance on oxygen because they are anaerobic, they have a smaller blood supply, and they don't have as much myoglobin, giving them a much paler color. And we often refer to them as white muscle. All right? So if you think about something like your Thanksgiving turkey, for instance, we can see that our Thanksgiving turkey really displays a lot of this well, right? So think about your turkey before it ends up on your dinner table, your turkey out in the wild, so to speak. The first thing that you probably know, even if you aren't a turkey ecologist, is that you know that there is no great turkey migration every year. And as a result of that, they don't fly a lot. Right? Turkeys aren't great flyers. They tend to do so only when they are startled. They're trying to get away from a predator, or if they're flying into the trees to go to sleep at night or something like that. And as a result of that, their flight muscles, their breast muscles, are quite large because they have to propel the entire bird, which is also quite large. But they also don't need a lot of endurance. They're short burst muscles, and as a result of that, we tend to find more fast twitch muscle fibers on turkey breast muscles. Turkey legs, by contrast, are going to propel the turkey through its daily life. It does a lot of walking, foraging for food, and things like that. And as a result of that, we find more of these slow twitch oxidative fibers in a turkey's leg muscle, and that's where we find the dark meat. If we were to contrast that with a Christmas goose, for instance, I don't know if you cook a Christmas goose or not, but if we were to contrast that, what you would find is that they do fly a long way. They are endurance flyers, and as a result of that, their flight muscles, their breast, have a lot of slow twitch oxidative muscle fibers, as well as their legs. You find very little white meat on a goose. So we can see these when we sort of look at different animals. It's important to note that when we look at the entire muscle, there are very few muscles in our body that are all slow twitch muscle fibers or all fast twitch muscle fibers. The majority of muscles in our body are a combination of these fibers. So if we were talking about this kind of in a real world context, we'd be talking about the proportion of muscle fibers. What is the proportion of slow twitch fibers to fast twitch fibers? All right. You would assume that in a muscle that's adapted for endurance activity, the slow twitch muscle fibers would predominate and there would be fewer of these. But to have none of these would be really quite rare. The opposite would also be true in a muscle adapted for burst activities. You would still have some slow twitch fibers. You would just have fewer of them than you have the fast twitch muscle fibers. All right. So very few muscles are all one fiber type or the other, but we can see a predominance of a certain fiber type depending on the activity or the demands being placed on the muscle. In addition to that, our muscles are also very adaptive, meaning that we can change the fiber type depending on the demands we are placing on the muscle. So if you start doing something like training for a marathon, you're going to see an increase in slow twitch oxidative muscle fibers and a decrease in the number of fast twitch glycolytic fibers. All right. Turns out that muscle fibers are very adaptable, and that leads us to the concept of phenotypic plasticity. One of the really cool things about skeletal muscle is that it's very, very adaptable. And we see this adaptability in these muscle fiber types really, really well. All right? We have the ability to change muscle fiber type depending on our activity. All right? So if I were to look at a muscle in your leg, let's just say I wanted to look at your gastrocnemius, and I wanted to look at the proportion of slow twitch fibers to fast twitch fibers, right? And then I wanted to put you on a marathon training plan, and I wanted to come back in 6 weeks, and I wanted to look at the proportion of slow twitch to fast twitch fibers. I would find that you've transitioned probably towards a higher percentage of slow twitch muscle fibers. All right? In biology, we talk about the way that you look. And I'm not just talking about your external appearance, but I'm talking about your internal appearance as well. We talk about that as your phenotype. Right? This is the way that you look. So if I were to look at your gastrocnemius muscle, and I were to look at the percentage of slow twitch fibers to the percentage of slow twitch compared to the percentage of fast twitch, that characteristic would be part of your phenotype. It's how you look, all right? And I could see that over time, as you started this marathon training plan, your phenotype would change, all right? We call that change in the phenotype, we call that your phenotypic plasticity. Pheno. Come on, Greg. Phenotypic plasticity. Okay, so your phenotype has the ability to change depending on different environmental activities, right? In this case, your environment changed because you started a training marathon, and your percentage of slow twitch fibers compared to your percentage of fast twitch fibers changed, all right? But it can change in regards to other things too, right? You go live in a cold climate, your phenotype is going to change. You move to a hot climate, your phenotype is going to change. You start to lift weights, your phenotype is going to change. Some of those changes will be visible, some of them will be invisible to the naked eye, but they're all part of your phenotype. Your phenotype is determined by your genetics, at least partly, right? We call your genetic makeup your genotype. So your phenotype is determined partly by your genetics. It's also determined by your environment. All right? So your environment is, in this instance, whether you're training for a marathon or not. Or your environment is whether you live in a cold climate or a hot climate, right? Or something like that. And then your genotype is going to make up the other part of that. So your genes at least partly determine what your phenotype ends up being. Sadly, for most of us, what this means is that if you're an athlete, it doesn't matter how hard you train. It doesn't matter what sort of an environment you put yourself in, you're still somewhat going to be limited by your genetic makeup, and that's going to limit your phenotype to some extent. So if you're a swimmer, for instance, you can train every single day, exactly like Michael Phelps trains, for instance, but unfortunately, because of your genotype, you're probably not going to perform at the same level as Michael Phelps performs. I'm sorry to inform you, and that's going to be true for most of us. But our muscle shows amazing adaptability in this regard, and it shows it with muscle fiber types really, really well. They respond quickly to change, and they respond in a very, very tangible way to change. All right? All right. So let's go ahead and wrap up our muscle lecture, and we're going to go ahead and start to talk about a couple of papers, and we're going to talk about those in class. So I've assigned those, and go ahead and read those and come to class prepared to do an assignment in class. Thank you.